For another application of solving linear systems of linear equations, let's think about analyzing a network of traffic. So suppose we have traffic flowing through a network of streets here, and we have, so these numbers represent how many cars per minute flow into the network. So there must be some street feeding cars into the network here. And so 20 cars per minute in here, 15 per minute come in here, and then 35 per minute leave here. This 35 isn't a coincidence, right? 35 is 20 plus 15. So as part of this setup, I'm going to assume that there are no cars that start or end their trip in this particular part of the street system, just because that if there are, that, you know, it takes a lot more work to model that situation, essentially. What we want to do is figure out what will traffic look like along these other streets in the grid, right? These three streets that we don't have labeled yet. How many cars per minute are flowing along those streets? So to figure that out, I guess we're going to have to name the things we don't know. And what we don't know are the flow rates along each of these streets. So let's call the flow rate this way x, and this way y. And, you know, intuitively, I've drawn these arrows for x and y because intuitively it kind of seems like traffic ought to flow that way and that way. But for this third road, we actually don't know where the net flow of traffic is going to be. We don't know if it's going to be flowing upwards or downwards. I guess I should say that all of these traffic flows are on net, right? In general, you could have traffic flowing both ways. So this is net traffic. For this last piece of road, we don't know which way net traffic will be flowing. So we kind of have to pick a direction. I'll write downwards for no particular reason. We'll call that z. But we'll keep in mind that if traffic is actually flowing the other way, that will just show up as z being negative. So, right, any of these flow rates could be negative, and that just means that the net flow is flowing against the arrow instead of with the arrow. All right, so how does this help the situation? Well, let's look at one of these intersections. So say right here. At each intersection, because there aren't any cars that start or end their trip in this part of the street grid, at each intersection, the number of cars flowing in must be equal to the number of cars flowing out. So at this first intersection, we have 20 cars per minute flowing in. Flowing out, we have x and also z, right? Because the way we have this drawn, z is going down, that's outwards for this intersection. So this intersection gave us an equation, and it happens to be a linear equation, of course. If it weren't a linear equation, I probably wouldn't be bringing up this application. All right, so we have two other intersections. So let's look at this intersection down here. At that intersection, let's see, we have 15 cars per minute flowing in. Also, we have z cars per minute flowing in, so plus z. And then flowing out, we have y. And then for our last intersection, flowing in, we have x and y, so x plus y. And then flowing out, we have 35. All right, you can see what we got is a system of linear equations. This isn't a homogeneous system, so let's rearrange this system so that all of our constant terms are on one side and all of our variables are on the other side. Just for consistency's sake, let's move the variables to the left and the constant terms to the right. So that's going to give us minus x minus z equals minus 20 for this first equation. Kind of silly to make everything negative, but that's life. For the second equation, we have minus y plus z equals negative 15. And then for the last equation, we have x plus y equals 35. Okay, now this is now it's in a linear system in the form that we usually write it in, so we can write the augmented matrix for this. We get minus 1, 0, minus 1, minus 20, 0, minus 1, plus 1, minus 15, 1, 1, 0, 35. Okay. Now we can punch this into a row reduction calculator or do the row reduction by hand. Fortunately for this one, doing the row reduction by hand wouldn't be that bad because so many of the coefficients are either 0 or 1 or minus 1. But just because I feel like it, I'm going to let the computer do the work here. So minus 15, and then 1, 1, 0, and 35. Okay, I hope I didn't make any typos. Oh, I did. I missed a comma right here. All right. So we get this reduces to 1, 1, 1, and then our augmented column is 35, 0, negative 15, which means we get x is 35 and z is minus 15. Okay, so that means that in this setup, actually nobody uses this road for some reason. 35 goes this way, and people actually go that way. 15 cars per minute go that way, which is a little counterintuitive. Did I make a typo? Let me double check. Let me double check that I typed in this matrix correctly. That's the window I want. Okay, minus 1. Oh, I did make a typo. No, I didn't. Minus 1, 0, minus 1, minus 20, 0. Ah, this is supposed to be minus. Minus 1, 1, minus 15, 1, 1, 0, 35. Okay, let's try that again. Ah, okay. See, this is totally different. This, this resulting form has a free variable. So this is going to be a totally different thing. So let's see, 1, 1, 1 minus 1. These are all zeros. Okay, this is more like what I was expecting. 20 and 15. Okay, so this first equation says that x is 20 minus z. Second equation says that y is 15 plus z, and z is actually a free variable here. So if we wanted to write things, vector style, x, y, z, we'd have 20 minus, let's use t instead of z, so t, and then 15 plus t. And if we wanted to, we could split these up. 20, 15, 0 plus t times minus 1, 1, 1. Like this. Okay. So one way or another, we've got 20 minus t across the top. So let me erase these. These are not right. So we've got 20 minus t across the top. Across the right hand side, that's y. We've got 15 plus t. And then the left hand side was t, going this way. Okay, so why is there a free variable? Well, something that this system doesn't actually lock down is, you could have these traffic flows into the system and have a huge number of cars just driving in circles, or you could have only these cars coming into the system and the streets be totally empty except for the cars coming in and then going out. Right? So what's undetermined about this system is that there might be sort of a constant circulation of cars around this triangle. Right? That's what the free variable is. Right? If t is some large positive value, that means, say, 100. That means we have 100 cars going this way and then that way. And then this negative here means that that 100 cars is going the opposite direction. So t is really representing the sort of static circulation of cars driving around this triangle. Since no one starts or stops their trip in this triangle, one wonders what those people are doing. Probably, if you were actually a traffic engineer, you would probably want to write all of these things as functions of time so that the flow rates into and out of this bit of street grid could vary over the course of the day. So sometimes you'd have people driving into it, and sometimes you'd have people driving out. Okay. Another situation where you have networks like this is in circuit analysis. You might have a network of, say, voltage sources like batteries. Like here we have a 5-volt battery, and resistors, right? We have some resistors here. So the unit for resistance is an ohm, which is symbolized by a capital omega here, and the unit for voltage is a volt, which is a V. What we don't know about this system is if you wire up this circuit, what actual current will flow through this circuit. So around each loop of this circuit, there's some current. So there's maybe, for some reason, I is the symbol for current. I think because C is taken by another electronic quantity called capacitance. So we have to have some other symbol for current, so physicists use I. So there's some current that flows around this loop, and there's some current that flows around this loop, so we could call that I2. You might object and say, well, actually, each leg of this circuit should have its own current because, right, the current through this middle is actually going to be different than the current through any of the other legs, so shouldn't there be a separate variable? Well, it turns out that the current through the middle is, right, current around this first loop is going down through the middle, and current around this second loop is going up through the middle. So it turns out the current through the middle is just going to be I1 minus I2, or I2 minus I1, depending on which way the current is going. So we actually don't need separate variables for each individual current, each individual leg of the circuit. We just need a current variable for each loop in the circuit. Okay, so with that in mind, what can we do? How can we actually figure out these currents? What we'll do is look at Kirchhoff's law. So Kirchhoff's law says that the voltage drop around a loop is equal to the impressed voltage. Okay, so what that means is in this loop on the left, we have 5 volts. And as we go around this loop, we can just write down the voltage drop across each resistor. Of course, to know the voltage drop across each resistor, you have to know the formula for voltage across a resistor. And that's given by Ohm's law. And Ohm's law says the voltage drop across a resistor is, so voltage drop is the current across the resistor times the resistance across the resistor. Right? And we know the resistances of all these resistors. So across this first resistor, the voltage drop is going to be the unknown current, which is I1, times the resistance, which is 3 ohms. I won't write the units, but the unit here is ohms. Right? Now we need to do voltage drop across the second resistor here. Right, for the second resistor, it's 4 ohms We have to multiply that by the current through this resistor. But remember, the current through this resistor, as we go around this left-hand loop, the current through this resistor isn't just I1. There's also I2 flowing through this resistor. So the current through this resistor is I1 minus I2. Right? We're going clockwise around this loop. I1 is going with us, so I1 is positive, and I2 is going against us, and so that has to be negative. Right? And then for the last resistor in this loop, it's 5 times, and then the current through this resistor is just I1. Okay, so this left-hand loop gave us an equation. Of course, the right-hand loop is also going to give us an equation, so let's write down that equation. Let me actually change this diagram. I'm going to put this voltage source the other way around, just so that it matches the way I do the current here. Okay, so starting at the positive side here, so we have 10 volts. So first we go through this resistor, so resistance of 2 times I2, because that's the current through this resistor. Okay, then this next resistor is 6 ohms times the current is I2 again, plus 4 ohms for that middle resistor times the current. But the current in our direction is plus I2 minus I1. Again, because I2 is going with us this time and I1 is going against us. So I2 minus I1. Now both of these are linear equations. So let's simplify it. For the first equation, we have 5 equals, so here's 3, 8 I1, and here's 4 more I1, so 12 I1, and then minus 4 I2. And for the second one, there's 10 equals, so there's, for I1, it's just this minus 4 here, plus, so here's plus 4, 6, 12, 12 I2. So when we write the matrix for this, we have to turn this around, right, because our augmented column goes on the right, so 5 and 10. So our matrix is 12 minus 4, 12. This might catch your eye, this left-hand part of this matrix here, because this is what's called symmetric, but that's actually just a coincidence. That's just because of how I chose the values for these. I happened to choose values for these resistances that made this part symmetric. So that doesn't always happen. That's a coincidence. Okay, so now we have this linear system. Now we can solve the linear system either by doing it by hand or just asking a calculator to do some row reduction if we're lazy. Not lazy, I mean, once you've done one row reduction, you've done them all, so your appetite for doing more row reduction is rather low. Okay, so we get this. This reduces to 1 and 1, so this is encouraging because, right, when we have a leading 1 in every variable column, or every column that corresponds to a variable, that means we're going to get a unique solution, which is kind of what we expect, right? If you actually build a circuit and then turn it, if you build a circuit and then turn it on, it's going to do a certain thing that is determined, right? It won't have some infinite number of possible behaviors. It's going to have one possible behavior. We hope. I mean, that's sort of what our intuition is. So it's encouraging to see that we're going to get a unique solution. And that unique solution is 25, 30 seconds, and 35, 30 seconds. All right, so the current around loop 1 is 25 over 32, and the current around loop 2 is 35 over 32. So that tells us how current flows through this circuit. Remember that to find the actual current through this, so along this bottom branch, right, around these, it's just the one current. So on the left, it's 25 over 32 amps through this resistor and this resistor. On the right, it's 35 over 32 amps through this resistor and this resistor. But for the one in the middle, we actually have to do a subtraction. Since I2 is the larger current, we'll put that one first. And let's see, I2 minus I1 is 10. So 10 32nds, or 5/16. And that's going to be upwards through this resistor because I2 was the larger one. So right, I2 is going up, I1 is going down through this resistor. I2 is bigger, so I2 wins. So this 5/16 is going upwards through this resistor.